the first colloquium of the semester of physics colloquium has a full house. That's just wonderful. Today we have the great honor and just great pleasure to introduce one of our own, in fact, a graduate student. And this is a very, very unusual. And I want to thank our department chair and the committee for making this exceptional exception to have a graduate student give a colloquium, because I think this has never been done before. And I was a graduate student at CEO Boulder. I want to say, what a special experience. If I get to pick again, I would be a graduate student again in CEO Boulder. And you will see, a graduate student like Chuankun makes an incredible scientific discovery, and that's the reason why he's today. And I hope you enjoy the colloquium today. Thank you very much.
Thank you very much, Jun, for the very kind introduction. And today is my great honor to tell you about our experimental effort building optical nuclear clocks, where we are essentially taking nuclear physics and metrology together. And I'll tell you why this is super exciting for both fundamental physics research and for practical metrology applications. Oops. Okay. Used to work. Since we are talking about clocks, essentially a clock is a device that uses a periodic signal to measure the elapse of time. Sorry. So if you walk past the JILA, if you walk past the Gamov Tower outside the physics building, you would have seen this pendulum clock out there. And the pendulum angle swings periodically with respect to time. And this time scale is on the order of seconds. Now, we could use this periodic signal as a clock, but this wouldn't be a great clock. Or modern atomic clocks, instead of using mechanical structures, we actually use the electron orbits inside atoms. And this oscillation happens at a much higher frequency or much shorter time period. And by doing this, we get a much more precise clock. So the best clocks today actually has systematic uncertainties on the order of 10 to the minus 19. Essentially, we are able to build sensors that has a 19-digit of accuracy. So by doing this, and also very importantly, these clock periods or frequencies are determined by a set of natural constants and how different atomic structures are made in nature. So this way, we actually can use these very precise sensors to test our understanding of fundamental physics. So for example, if there is a dark matter floating around in the lab, you might be able to see it interact with the clocks and produce very tiny shifts on the very precise clock measurements. Now, clocks are also very useful for synchronization, for keeping track of time. So if we use clocks to synchronize different telescopes across the world, we can do a phase coherent astronomy observation. And actually, people used that a couple of years ago to take the first picture of a black hole. So in these clocks, we actually are dealing with electronic transitions. So the transition energies are about 1 electron volt, which corresponds to wavelengths on the order of 1 micron or 100,000 nanometers. Now, for these electronic transitions, we can build a very good coherent visible or infrared laser sources on tabletop systems. But if we zoom into the atomic nucleus, we can see that in this nucleus composed of protons and neutrons, we essentially also have a similar energy level structure. But the difference is now we're talking about energy levels on the order of mega electron volt, so 1,000,000 times higher with a 1,000,000 times shorter laser wavelength of about 0.001 nanometers. So typically, people can generate people can generate these kind of X-ray or gamma ray photons with these synchrotron light sources. However, these are still broadband, not nearly as coherent as our tabletop visible laser sources. Now imagine if we can take this visible laser light and use it to drive nuclear transitions, and then we would be able to open up a new field of precision measurement using nuclear energy levels. So that's what we are going to do. That's what we are going to tell you about in this talk. But first, if we go back a bit in history, we can see that people actually started doing nuclear physics, nuclear spectroscopy in an incoherent way a long time ago. So essentially, if we start with a radioactive source like cobalt-57, it decays down to iron-57 via radioactive decay process. And in this process, some of the nuclear excited state actually gets populated. And the gamma ray photon decay of this nuclear excited state can actually be used to excite an absorber made out of the same material. And Rudolf Mosbar actually was awarded the Nobel Prize in 1961 for this spectroscopy technique. A very unique character of this Mosbar spectroscopy is that one can observe very narrow transition lines, essentially free from Doppler broadening. Now, this is very similar to what we do in modern atomic AMO systems, where we use optical lattices or lasers to confine the light, confine the atoms very tightly. And in Mosbar spectroscopy, actually, we can rely on the crystal structure inside a solid to provide the same type of confinement where we can eliminate the Doppler broadening and the recoil shift. So these Mosbar spectroscopy, nuclear spectroscopy techniques can be very useful for fundamental physics. Here I'm showing you one example. Back in 1960, Pond and Repka decided to use the Mosbar spectroscopy line to test the general relativity. So essentially, they used the Mosbar spectroscopy source and target separated across a 22-meter tall tower. And one can see that is exactly as what people predicted through general relativity, that as photons, gamma ray photons travel from bottom up, going upstairs across this 22-meter tall tower, we will see a redshift of the photon energy. Now, in modern atomic clocks, we have much higher resolution than that. We can even see this same kind of gravitational redshift or relativistic time dilation effect across a single millimeter of atomic ensemble. And so you can see that there is always a kind of a abstract nuclear atomic connection here, in that we use the different physics platforms to measure the same kind of fundamental physics phenomena caused by general relativity. Now, of course, this is not a direct connection, and today we're going to talk about how we build a direct connection. We are going to take this modern atomic clock technology and use them into bring them to nuclear physics, and we will build a nuclear-based optical clock. So how do we build this nuclear clock? Actually, we plan to do it in 3 steps. First of all, we will pick our favorite nuclear transition, which for now we can think of this as essentially just a 2-level energy system. And next, we bring a laser over. If we shine the laser on the nuclear transition, onto the nucleus, and if we see the nucleus starts fluorescing, we know our laser is on resonance with our nuclear transition. And then in the final step, we bring a frequency counter over, and if we can measure the laser frequency very precisely, we essentially now have a frequency reference that's directly derived from the nuclear energy levels. So we have a nuclear-based clock. Now, for this nuclear transition, we picked a very unique nuclear isotope, or the thorium-229. This is essentially because most of the nuclear transitions are indeed in this kilo or mega electron volt energy level, where it's very difficult to build coherent laser sources, or we don't have coherent laser sources today. But thorium has this uniquely low-lying energy transition that is about 8 electron volt, so where we can still build state-of-the-art vacuum-ultraviolet lasers. And also, its lifetime is conveniently located very similar to atomic shell transitions that have already been used for atomic clocks. So it's an ideal candidate for making this nuclear-based optical clock. And for the laser and the frequency counter, we actually combine these 2 devices into one in our lab. This is a phase coherent vacuum ultraviolet frequency comb that we build in our lab, and I'll go into more details of how we construct this device. So this nuclear clock is super exciting for us, because now we get a lot of new opportunities for doing fundamental physics and applications. So first of all, this could be a very accurate clock, because this is partly because we have a very high quality factor of this oscillator. Essentially, once we can excite this nuclear transition, we can measure the coherent oscillation of it, or it oscillates coherently for about 10 to the 19 cycles before it decays down. So we can measure its transition frequency very accurately. And also because we are now probing a nucleus, which is very well shielded by the outer electronic shell. So it's very resistant to external perturbations. And we can build a clock with a potentially 10 to the minus 19 level of accuracy comparable to today's best atomic clocks. And moreover, we, just like in Mosba spectroscopy, we can embed the thorium atoms into a solid state crystal lattice. Now, because we can embed a lot of a large microscopic amount of thorium atoms inside this crystal, we can probe them all in parallel. So we can average down the statistical noise very quickly, and this gives us a high clock stability. But also, now through the lattice confinement, we don't need to do the sophisticated laser cooling and trapping anymore. So a solid-state nuclear clock could be much more robust, much simpler, and we can really use it for portable metrology applications outside the research labs. And also, the nuclear clock gives us a unique probe for fundamental physics. This is essentially because we're now taking precision measurement tools with a potentially sub-millihertz resolution, and we are using it to examine nuclear energy levels that are on the order of mega-electron volt. So we get a huge enhancement for fundamental physics searches, such as variations of fundamental constants. And moreover, essentially, we are unlocking a new quantum degree of freedom inside atoms. So now we can study electron-nuclear couplings in a fundamentally new regime. So this is such a great concept. Why hasn't anyone built it yet? Well, it turns out that until last year, the transition energy wasn't known very well. So here I'm showing you several different measurements, essentially from past about 40 years of experimental efforts to pin down the transition energy. And you can see that even if we take the weighted average of the most recent measurements, the transition uncertainty is still on the order of or the uncertainty of this, where this transition is still about 2.1 nanometers, which corresponds to about 100 terahertz of uncertainty region. So this transition is a millihertz transition. So if we're searching for such a narrow transition in this 100 terahertz uncertainty range, we're really searching for a very small needle in an astronomically large haystack. And this makes the experiment very challenging. Fortunately, last year, there was a very important breakthrough where people were able to use an accelerator facility in CERN to populate some of the thorium nuclear excited state. And there, people were able to observe the fluorescence decay of this nuclear state for the first time, where you can then measure the fluorescence photon energies, photon wavelength by a grating-based spectrometer to higher precision. And also, this allows people to test the fluorescence-based detection setup. So now, inspired by that, earlier this year, we've seen two successful laser excitations of this thorium-229 nucleus, where people were able to observe a single nuclear excitation, single spectral feature in these nuclear excitation measurements. And based on wave-meter calibrations or wavelength-based calibrations, people were able to measure the transition wavelengths to higher precisions. Now, the reason why these spectral features are limited still to 10 gigahertz of width is because we face a time-frequency dilemma in making these VUV lasers. So essentially, in this VUV, we don't have a direct lasing medium. So what we needed to do is to use a nonlinear optics method to generate the vacuum-ultraviolet light. So for that, we want a very short laser pulse. Therefore, we get a very high laser peak power. But as we know from Fourier transform, this short laser pulse necessarily corresponds to a very broadband spectrum. So we can't really use this broadband spectrum then to do high-resolution spectroscopy. So our solution to this is to combine ultra-fast and ultra-precise in a frequency comb device. So the basic idea goes as follows. If we add a second laser pulse over, we see that these two pulses actually now start to interfere, and we get a ripple pattern in the frequency domain. Now, if we add more and more pulses, and very importantly, we need to add that in a phase-coherent way, that means our phase delay or the phase difference between each pulses and the time delay between each pulses need to be extremely well reproducible. And the Fourier transform then gives us a equidistant spectral lines in the frequency domain. So essentially, this is our frequency comb, which has a phase coherent positioning time and corresponds to equidistant spectral lines in frequency. And actually, this frequency is exactly the the frequency separation between adjacent comb lines is exactly the repetition rate of the laser pulse 1/delta t here. So this very short femtosecond laser pulses coming from frequency comb could be very useful. Essentially, we could take these femtosecond laser pulses, focus them down to a gas target, and generate even attosecond pulses with them. And so this is forms the basis of the Nobel Prize last year, where people were using the high harmonic generation process to study attosecond physics. And also, the equidistantly spaced spectral lines essentially can serve as a ruler of light, where you can use them to precisely measure laser frequencies. And this effort was awarded the Nobel Prize also back in 2005. So in our experiment, we actually wanted to take advantage of both the time and the frequency domain characters of the frequency comb. In the in the frequency domain, we stabilize our frequency comb to the strontium optical clock by linking one of the comb line to the strontium clock transition. And then we take the femtosecond laser pulses and use that to drive a high harmonic generation process, where we essentially coherently upconvert our frequency comb to its 7th harmonic in the vacuum ultraviolet frequency domain. And then we use one of the comb line to drive the thorium nuclear transition with thorium atoms embedded in a crystal lattice environment. So this way, we actually establish this direct frequency connection from our thorium nuclear transition back to the strontium atomic clock. And I want to take this opportunity to acknowledge groups of people who built our very nice JILA strontium optical clock and stable lasers, and also our friends and collaborators at IMRA Ytterbium comb team who helped us tremendously in building the infrared frequency comb. So if we look at the parameters more closely, we can find that this is actually a very challenging experiment technically, because for precision spectroscopy measurements, we actually want a very high comb repetition rate of the pulses on the order of tens or hundreds of megahertz. This is partly because we want a very wide space, the frequency comb lines. Also, we wanted to check the optical phase very frequently to make sure that our frequency comb stays phase coherent. But for driving ultra-fast strong field physics, we actually need a very high laser peak intensities on the order of 10 to the 13, 15 watt per centimeter square. Now, combining very high laser peak intensities together with very high laser repetition rates with reasonable pulse durations and focusing parameters essentially means we need a very high laser average power on the order of tens of kilowatts. Now, this is very challenging to do or difficult to do with active amplifier technologies. So what we choose to do in our experiment is to use a passive resonator to build up the power, which is our femtosecond enhancement cavity. Essentially, we see that frequency combs, they have equidistant spectral lines in the frequency domain separated by the comb repetition rate. We know the enhancement cavities have roughly equidistantly spaced longitudinal modes separated by the cavity-free spectral range. So if we match every frequency comb line into one of the cavity modes, we can enhance the frequency comb altogether inside the cavity. And on the right-hand side, I'm showing you the cavity-enhanced high harmonic generation in progress. You see that we have a bright plasma. That's when our infrared frequency comb is focused into a gas jet. And this white trace is actually left there by the high harmonic beam ionizing some of the residual gas inside our vacuum chamber. So this cavity-enhanced high harmonic generation for XUV comb production actually took more than 20 years of development effort. The early ideas really dates back to early 2000s even, where people started to test out how one can enhance a femtosecond frequency comb with enhancement cavities. Back in 2005, people already demonstrated the first XUV combs where the comb power is about, where the available comb power is about 100 picowatts. But over the years, we've seen a lot of progress made in this field. We've seen that people can actually use XUV comb structure for frequency for spectroscopy at even 82 nanometers of wavelength. We've seen that we can control the phase noise in this XUV comb generation process very well, such that we get coherences longer than seconds. We've seen that we will learn how to phase match these XUV comb generations inside the enhancement cavities. So today, we're building on top of all this knowledge that we learned to make and we made a tunable VUV frequency comb that's tailor-made for searching for this thorium, driving this thorium nuclear transition with more than milliwatts of output power. So now we have a great laser source. We also need a spectroscopy target. What we choose to use is this thorium-229 doped in calcium fluoride that's grown by our collaborators and friends in Thorsten Schoen's group at TU in Vienna. And actually, these solid-state samples also of thorium also took more than 10 years of development efforts. The early ideas really dates back to these proposals more than 10 years ago. But people over the years have overcome a lot of technical difficulties in growing these crystals. So so here I'm showing you the actual crystal installed in our setup, where the red arrow is pointing to where the crystal is. And you can see a white line going through the crystal. That's our laser beam exciting some of the color centers and giving us some fluorescence in the visible light. So essentially what we do in the experiment is we shine VUV laser onto this thorium-doped crystal for about 400 seconds. And then we turn off our VUV laser and collect the fluorescence photons emitted by the crystal, emitted by the thorium nuclear transition inside this crystal using a parabolic mirror. Now, these photons are sent through a set of dichroic filters and eventually to a photomultiplier tube where we can count individual fluorescence photons. And if we were able to successfully excite the thorium nuclear transition, we will see a higher photon count rate on our photomultiplier tube. So coming back to the spectroscopy, in our frequency comb, we actually have many frequency comb lines. We can assign an integer mode number to them, and their optical frequencies can actually be described by this simple equation where you have a common offset plus a larger integer mode number n times the comb repetition rate, which is the gap in between the comb modes. Now this integer mode number n is actually a very large number for our frequency comb. It's on the order of 10 to the 7. And then our nuclear transition would be a narrow line sitting in between these comb lines. So if we zoom out to the see the full coverage of our VUV spectrum, VUV comb, we can see that our VUV comb actually covers a very wide spectral range, even fully covering the uncertainty range that we know from last year, the measurement done in CERN. And now, with the most recent uncertainties reported earlier this year, we can still zoom in, and we still have hundreds of comb lines there that we can scan them. But we can scan them, all of them in parallel to cover essentially the gap in between adjacent comb lines by slightly changing our comb repetition rate. So here's what we did in the experiment. Essentially, we are scanning the comb repetition rate here by about a few hertz. But since we have this larger integer mode number n, we actually are covering the entire optical uncertainty region where the nuclear transition could be. So the data, so in the raw data, you can see here that there are a couple of distinct spectral lines that we are highlighting in blue here. And if we look at the time domain behavior of this transition, these spectroscopy features, we can see that they indeed actually last for a very long time, about 200 or longer than 200 seconds, which is our observation time. So these are very long-lived nuclear transitions that we are exciting in our solid-state environment. And now we can zoom in to one of the transition lines and actually study the transition line shape. So again, here horizontal axis, I'm showing you in the comb repetition rate. But if we multiply by this larger number n, go back to the optical transition frequency domain, the transition line width is actually about 300 kilohertz. And this is, we think, essentially still limited by our line with our VUV frequency comb. And we have some ideas on improving that further. If we look at the time domain, decay of this fluorescence, we can see that it actually has a very long lifetime, or it follows very well, follows a single exponential decay very well with a very long lifetime of about 641 seconds. Now we also wanted to determine the absolute transition frequency of this transition. So essentially, we know from our Coulomb equation that if we just do one measurement, we actually don't know which Coulomb mode number n was used for exciting the nuclear transition. So our goal is to determine this integer number n by doing a couple of different measurements, and then we can set up a couple of different equations where we can essentially solve this math puzzle and figure out where the nuclear transition is. So we did that with 3 different measurements, and we can see that once we solve for these integer mode numbers, we can scale the measurements back to optical transition frequencies, where the different measurements of the same transition line indeed agrees very well with each other. And the horizontal axis now is essentially a direct readout of the transition optical frequency. So you can see our frequency column also serves as a frequency counter for us to directly measure optical transition frequencies. Now you saw that we had a couple of different spectroscopy features. We actually performed this absolute frequency determination for 4 of these dominant lines, and their frequencies and line shapes are shown here. So the reason we have a couple of different transitions is because we actually have a quadrupole interaction, electric quadrupole interaction between the nucleus and the crystal. So we have this, or we expect to see actually 5 splittings. And the line E is missing here because it's a weaker transition due to the smaller CG coefficient. So its intensity is expected to be about factor of 10 lower. Nevertheless, we can determine the absolute transition frequencies of these 4 lines, and then we can predict where line E should be. So if we go back with our experiment and actually check where the line E is expected to be, indeed we see some spectroscopy features there, and its transition frequency matches very well, matches within uncertainty region of where we expect it to be. So now with that, we can also report a frequency ratio with the thorium-229 nuclear transition and our strontium optical clock. So this frequency ratio is measured precisely to the with uncertainty on the 13th digit, and we haven't evaluated the systematic uncertainty in this work, but in this work we are taking the data in 150 Kelvin Earth magnetic field in thorium-doped fluoride crystal. So we care about this kind of frequency ratio measurements because essentially we are getting this unitless number that doesn't depend on our choice of frequency or time units. And this is a direct measure of how different type of transitions that depends on strong force and Coulomb force, and compared to atomic transitions that mostly depend on Coulomb forces, how strong their relative ratios are. So this would give us a lot of insight for fundamental physics. Now, we also try to understand the quadrupole splitting better. So essentially, we know from that in our crystal lattice, the neighboring ions essentially produces a electric field gradient at the position of the thorium nucleus, and the thorium nucleus has a electric quadrupole moment that could align in different angles, in different directions in this electric field gradient. So we can write down the Hamiltonian that describes this interaction, where the Q is the nuclear quadrupole moment, and the electric field gradient can actually be determined by 2 parameters, VZZ, which is a principal axis component, and eta is an asymmetry parameter that describes how asymmetric this electric field gradient is. So by fitting our experimental data to this Hamiltonian, we can then extract these set of parameters where eta is purely the asymmetry parameter that purely depends on the crystal structure, and we can get the QVZZ product. But they depend both on the nuclear properties and the crystal properties. So if we take the ratio, we can actually get a number that is independent of the that is only dependent on the nuclear properties. So now this ground excited state quadrupole moment ratio actually tells us something about the nuclear structure. So this ratio is first measured in our lab frame, but we know that the nucleus has some angular momentum, so it's rotating around and gives us an averaging effect. So if we transform back to the body fixed frame of the nucleus, we actually can learn about the quadrupole moment, quadrupole deformation ratio between the ground and the nuclear excited state. Now you can see that the ratio is actually very close to 1, indicating that the ground and excited state, the quadrupole deformation is about the same, but we can measure this very small difference very precisely. And this combined with some other nuclear physics parameters, we can then use a purely geometrical model to deduce the corresponding nuclear volume in the ground and excited state. Now, people typically assume that in these nuclear transitions, your nucleus looks like an incompressible liquid droplet, where the ground and excited state volume would stay the same. You can see that this is indeed a very good approximation, but we are now at the measurement uncertainty where this approximation starts to break down. So the reason we care a lot about this kind of nuclear structure is because actually in the nucleus we have this Coulomb repulsion term that is proportional to some fundamental constants like the fine structure constant alpha. We also have strong force binding the nucleons together. So essentially, if we look at the nuclear binding energy for the ground and excited state, the change in the Coulomb energy and the QCD binding energy, they add up canceling, almost canceling each other. This leaves us a very small energy of 8.4 electron volt. That's our nuclear transition energy. But from the geometrical model, we can calculate that the Coulomb energy difference between the excited and ground state is actually about 50 kilo electron volt. So now, if fine structure constant alpha is changing slightly, this would change the nuclear transition energy proportional to the 50 electron volt Coulomb energy difference. So essentially, we get a very large enhancement for sensitivity to fine structure alpha variation over time by monitoring our nuclear transition. And this enhancement factor is about 6,000. So now this is only evaluated with a pure geometrical model up to the quadrupole moment. Of course, there could be even higher order moments present in this large nucleus, which we still don't know about. For example, if there's octupole moment, it might deform the nucleus in a different way. And there are theoretical investigations on how these high order moments may still change the sensitivity to alpha variations. So there's another type of enhancement for fundamental physics that we gain in these nuclear clocks. Essentially, because in nuclear clocks, we are sensitive now to the quark-gluon physics in the standard model, while in atomic clocks, we are mostly caring about electrons and photons. So this could give us a very highly enhanced sensitivity for things like a variation of the QCD scale, lambda QCD. Now you can see that here I'm showing you the orange line is corresponding to our first spectroscopy result of our nuclear transition with even 300 kilohertz line width. And for lambda QCD variation sensitivity, we are already surpassing existing state-of-the-art optical atomic clocks. Now we care a lot about these fundamental constant variation because this actually opens up a new window for us to test theories about dark matter. Essentially, from astronomical observations, we know that our universe is made of has a lot of dark matter than the ordinary matter that we are familiar with every day. And this dark matter, some certain types of this dark matter, especially this ultralight dark matter that we're talking about here, actually has a very low mass. And they oscillate at a Compton frequency that is relatively low, or their wavelength is long, so they are coherent on the, they behave like classical fields on our detector scales. So essentially, this dark matter could oscillate could behave as a oscillating classical field that could interact with, say, our nuclear transition and distort our nuclear transition line shape or add sidebands to our nuclear transition. And so by analyzing this line shape of the nuclear clock transition, we can actually also put bounds to or test some of the hypothesis for dark matter. And here again, I'm showing you the orange line being our projected sensitivity for dark matter, for this particular dark matter Suppose now we can maybe push our comp line, or our spectroscopy line width from 300 kilohertz to 1 hertz per second in the near future, then we will be sensitive to a very large parameter space of this in this dark matter search. Now, besides fundamental physics, we can also learn a lot about crystal structures. So we've seen this quadruple splitting. Essentially, this quadruple interaction Hamiltonian gives us a splitting between the transition lines dependent on the local electric field gradient. But also, we have essentially a monopole interaction where the finite charge radius interacts with the local electron charge density, and this could shift all the spectral lines together. So what we did in the experiment is we actually performed a temperature scan where we changed the crystal temperature by about 150 degrees. And we monitor their transition frequency change. Now, here I'm showing you a zoom-in view of the different transition lines. And you can see, indeed, their splitting shifts. And the red line here is average frequency. And you can see that their average frequency also moves around with respect to time. Sorry, with respect to temperature. So again, by fitting back to this Hamiltonian, we can extract the crystal lattice parameters of the QVCC product. And of course, we know that the nuclear quadrupole moment doesn't change with temperature. So this actually gives us a very good measure of the local electric field gradient change with respect to temperature. And also, this eta parameter, which indicates the asymmetry of the field gradient, also changes with respect to temperature. And that's essentially corresponding to an anisotropic thermal expansion of the crystal along different crystal axes. So we can also extract some estimates about the local charge density based on local electron charge density at the nucleus through this monopole interaction and how that changes with respect to temperature. OK, so now in the last couple of minutes, I want to switch gears and tell you about a different effort that we are pushing towards for practical metrology applications. So essentially, all the data I showed you were taken with these thorium-doped calcium fluoride single crystals. And they work very well. They are grown with a more or less conventional crystal growth technique, where these crystals, as grown, are on the order of centimeter size scale. So the problem is that to grow these large crystals, we actually need a lot of thorium material, thorium-229 material, to get a very high doping concentration in these crystals. And now thorium-229 is a radioactive material. It's 100% produced by human beings. And so we actually only have a very limited amount of thorium available on this planet. So so in Boulder, we actually created this thorium fluoride vapor deposition setup where we essentially load a small amount of thorium fluoride into a crucible, and we heat it up to perform thermal vapor deposition. So using this technique, we can create targets much smaller with a diameter on the order of 50 microns and with a thickness of essentially about 30 nanometers. So these tiny targets allow us to use the very rare thorium-229 materials very efficiently. And also, these targets have very low radioactivity. So the radioactivity is about a fifth of Bodana. So you would not be, so this would relax a lot of the radiation safety measures for using a nuclear clock. And the caveat is that we haven't been able to observe the narrow nuclear transition line yet with our frequency comp system. But we got very powerful friends at UCLA. If you know, you might know that Professor Eric Hudson was actually also a former CU physics grad student working at JILA. And so we sent over our thorium fluoride samples over to UCLA. And here's one of the samples we sent over to us. This is our number 22 sample. So you can see that we failed more than 20 times before that. But now this sample actually worked. And there's another sample that we sent over on a different substrate. So you can see these two different lines represented the spectroscopy results from these two samples on different substrates. And indeed, they both show up exactly at where you expect the thorium nuclear transition to be. And the transition line, the spectroscopy line width here is also about 10 gigahertz, and that's still limited by the broadband laser system used in UCLA. So also we have some remaining mystery in these samples, essentially for the bulk crystals, either in our calcium fluoride or in lithium strontium aluminum fluoride grown in UCLA, we all observe a lifetime on the order of about 600 seconds. But in these thin films, we actually observe a much shorter lifetime, about 160 seconds. And we don't fully understand that yet. We have some theories that explains maybe part of it, but there are still some more understandings to be made. So we are super excited about this because there are a lot of exciting applications with the thorium fluoride thin film target. So first of all, you can imagine because of the very high density of solids, now we can pack essentially on the order of 10 to the 7 thorium atoms inside one wavelength cubed volume, or 150 nanometer cubed volume. And this gives us a very unique system where we have a lot of quantum emitters packed very tightly in space, and then we can use it to study collective effects like superradiance and quantum optics in a new platform. And moreover, since we can fabricate these kind of thin film targets, we are considering or thinking of ways how to integrate this with a nanophotonic structure, waveguides, cavities that could potentially enhance our detection of the nuclear transitions. And eventually, we wanted to perhaps integrate these thorium fluoride thin films together with on-chip detectors, say, and make a fully integrated nuclear clock on chip. And actually, we are working a lot with the NIST SSPD team down the road. And Siwu Nam actually approached us back in 2018, and we had a lot of discussions of how we might be able to use these very nice superconducting nanowire single photon detectors for detecting the thorium nuclear transition. Now, sadly, Siwu passed away not so long ago, but we're still working with Galen and Dilip in pushing towards this direction. We hope that eventually we'll have a nuclear clock fully integrated on chip that could be available for everyone for precision metrology, any precision metrology projects that you want to do. So with that, I hope that I showed you that we are combining precision laser metrology techniques, nuclear and fundamental physics, and ultra-fast laser science tools together to create this thorium-based nuclear clock. And our paper will actually be published as the Nature cover story next week, a week from now. So, and in the last couple of minutes, I showed you how we are also pushing towards this thorium fluoride thin film platform for scalable production and photonic integration of a thorium clock. So with that, I would like to thank you again for your attention and acknowledge our team, especially everyone in the team, but especially Professor Jun Ye. And also, this work couldn't be done without our help from our JILA friends at the instrument shop, electronic shop, CAC Lab, and our friends from CU Physics and Chemistry departments, the CU Radiation Safety Office. Thank you, and happy to take any questions.
Lots of time left for questions, if there are questions. James seems like I want to ask one.
So do you have a guess, or do you know why, when you change the temperature, the line shift? What's the physical origin?
Yeah. So actually, let's see if I can go back to the slide. Now I need to share my screen again. So, okay. Essentially, actually, the shift kind of mostly, we think mostly it comes just from thermal expansion, and it roughly makes sense. You see that we actually get, I guess, so the thermal expansion coefficient is on the order of 10 to the -6 per Kelvin. And then I think essentially, if you look at this monopole shift and quadrupole splittings, their total energy scale are on the order of gigahertz. So essentially, it comes down to if you have a 10 to the minus shift of this about 1 gigahertz total interaction energy, that comes back down to about 1 kilohertz per degree also, which is about what we observe in these line shifts. So we think it aligns pretty well with just thermal expansion of the crystals.
Take that to mean that you're essentially changing the temperature, which changes the quadrupole electric field experienced. And if you take the average, the appropriately weighted average of all these transitions, you become insensitive.
So if you take the average the transition frequency, you are not sensitive to the quadrupole interaction, but you become sensitive now to the monopole interaction, because the ground and excited state charge radius of the nucleus is different, so the charge density still changes things. But now one interesting thing is that you might have seen this line appears to be a little special, where the temperature dependent shift is less compared to the other lines. We think this is accidental cancellation between the monopole and the quadrupole interaction terms. So this less sensitive line might be a good candidate for a clock transition line, where it's less sensitive to temperature shifts.
Opportunity to engineer a crystal structure where to cancel exactly this line for multiple clocks. Yeah. Hold on. Yeah.
Amazing work. Is kind of, different from the solid state platform. Is there any route in the near future to trying to interrogate the same transition in a trap using trap thorium ions?
Yes, so it's still a difficult experiment, right? Because in the solid state sample, we have 10 to the 15 thorium atoms that we can interrogate in parallel. Now, if you go into an ion trap, then you have a lot less thorium ions. So one could imagine building a little better lasers, and now with either CW lasers or with frequency comps with higher average powers, and one could imagine exciting the nuclear transition in ion trap as well, but it's still difficult.
Thank you.
Yeah, I must have misunderstood, but there was a slide where you said you showed the width of the line, which was a few hundred kilohertz, but then you were saying the lifetime is a few hundred seconds.
Yes.
So is that? It seemed.
Yeah.
Am I misunderstanding how those are inconsistent? Or?
Yeah, so essentially we think the 300 kilohertz, or the 300 kilohertz is the actual spectral feature we observe in the experiment. We think that's more an indication of our laser line with being about 300 kilohertz, but the underlying transition is narrow. Now, the transition lifetime is about 600 seconds, so very long, very narrow transition, but we could also still have inhomogeneous broadening in the crystal field, in the crystal environment, which we don't know exactly yet, but there are theoretical predictions saying that this should be on the order of a few hundred hertz to kilohertz level. So likely we're not seeing this crystal limited transition inhomogeneous broadenings yet.
So somehow the lifetime you're extracting not from spectral measurement, but from just watching it decay or something?
Yes, yes.
Oh,
yeah,
I
so yeah, we actually watched it for about 2 hours.
Okay. And the other question is, what's the picture of these different states? Is that well understood from nuclear physics? What the different levels that you're interrogating?
So there's a different.
I didn't understand the.
Yeah.
Like, should I just think of it as a liquid droplet with different configuration?
So these different states, or
yeah, these are the nuclear states. Yeah.
Yeah, so these are actually essentially just the different alignment of the quadrupole moment with respect to the local electric field gradient. So this is not an internal nuclear structure, but since we probe the nuclear transition inside the crystal, we also have, or we also see line splittings through this interaction. Yeah.
Okay. Thank you.
Seems like the field should be on a thesis complete, so that until you get your laser narrow, you cannot graduate. Because it should be the line should be as narrow as microhertz.
Yeah, 1 was.
A few years to go.
Actually, I had a question. Can I? So just to segue from that, if you go back a couple of slides from where you are, I think there was that decay curve that you had. I think that's probably counts versus time. And there's a little bit there that was missing for, I think here. Yeah.
Yes.
Did you fall asleep
Yes.
at around 2000 seconds? Or did you, is it interesting physics? Just
Okay. No, this is purely technical. This is actually, the problem is we didn't anticipate that we will get this high count rate, so we programmed our deck to automatically stop after collecting some number of counts, and then we're like, maybe it's worthwhile to take a little more data after that.
Yeah, since you already shown like in 1960, people can generate, excite the other nuclear by the same nuclear. Is it possible to make CW laser by thorium? For example, you tune the band gap equal to a nuclear transition and then excite it.
Yeah, so in principle, I would say yes. If you find a way to excite the nuclear transition into the excited state and maintain a population inversion there, why not? I guess I currently don't have a way to really do that. I think there are actually proposals for how one can maybe run that by generate that kind of population inversion by electron scattering.
So you mentioned I think the Earth's magnetic field. So you have a Zeeman effect, and so how sensitive are you to magnetic field changes? And could you do some form of magnetic resonance spectroscopy then, actually, and probe chemical processes or crystal field effects or effects of defects in the crystals you embed the thorium?
So our sensitivity, since we're dealing with this nuclear transition, or it's just the nuclear alignment to the magnetic field, so it's about, I think, about a kilohertz per Gauss through the nuclear magneton. So can we do some magnetic type of spectroscopy? We can do this kind of essentially with these different quadrupole moments. You can imagine putting a microwave in and drive the transition between these two different M states, different alignment of the quadrupole inside the electric field gradient by coupling to the nuclear magnetic moment. Yeah, so one could actually do that, and I guess we're actually thinking about using that to potentially detect our nuclear excited state population. The difficulty is that there is because we are working with this thorium doped crystal where we don't have a lot of atoms, so doing spectroscopy directly on the microwave transitions, the signal to noise ratio will be relatively low due to very small amount of atoms we have.
Yeah, okay. Yeah. And just a quick second question, a very practical one. The thorium fluoride is what I know is used as a mirror coating, actually, optical mirror coating. Was that why you chose it, or because it's easy to make thin films, or what was then the motivation for you for switching to thorium fluoride?
Yes, partly. Actually, thorium fluoride is easy to evaporate because its evaporation point is relatively low, or vapor pressure is relatively high. And then also, if you look at the transparency of different materials, you find that mostly fluorides are transparent in the vacuum ultraviolet region. So we decided to try out the thorium fluoride. Actually, later we found out there are some literature saying that thorium fluoride should be indeed transparent at this VUV frequency. So other thorium materials are harder to produce, not transparent in this wavelength. So thorium fluoride is kind of a natural choice.
So maybe this is perhaps not really up your alley, but I'm looking at your picture over there, and you have this J equals 3/2 level and the J equals 5/2 level, and they're separated by from a nuclear physics point by something which is tiny, 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 tiny. Is there any understanding of why that should happen? Is it just blind chance, or is there, I mean, what are the nature of the states? What's known about that?
As far as we know, it's a accidental cancellation. So in the ground to excited state, I showed you that the Coulomb energy actually changes by about 50
no,
keV.
I mean, you have these big differences, but is it?
But somehow the strong force change accidentally cancels that. We don't know if there is a deep underlying reason for that. I think there are some nuclear structure theories predicting that it should be a low-lying transition, as in that it should be, there are some favorable properties that it should be like a transition below kilohertz, below kilo eV, but nothing that we know that indicates.
I can't imagine you could do any kind of a calculation that would get you, a number which is smaller than a kilohertz, than a KeV.
Yeah.
I mean, we have our resident nuclear theorist here also. So, so are there lots of these states around, or is it just an accident? This is the only one.
This is the only one that we know. Yeah. Oh.
14.
No, 70 something. Yeah. The problem of the uranium transition is that its lifetime is longer than the age of the universe. So if I wanted to graduate at some point, maybe
No, but we use Marcus Raschke's technique. You do NMR. When you drive the transition, you do NMR.
Okay.
And I think, again, maybe we should go to quantum optics class by James Thompson. Professor James Thompson teaches superradiance. Maybe we should think about this idea of superradiance seriously. Right? Put all the nuclei in the excited state and have them superradiant, and that's a laser at a 148 nanometer.
Okay. I'll take that class next semester.
We still have a couple minutes.
Thank you for the great talk. So you've mentioned that this nuclear transition has a very high lifetime of 600 seconds. It seems to me that if you wanted to lock a laser to this transition via, say, like frequency modulation, that this would be quite a challenge because you could only feed back very slowly, and maybe you would need a very long coherence time on the laser. Is that the case?
That's a very good question. I think yes, it is the case to some degree, and one can actually make a very good long coherence time lasers thanks to our stable laser team at JILA, and so yeah, I think you do need to start with a very long coherence time narrow line with the laser, and then you can indeed generate these kind of lasers by very good, say, silicon cavities.
Thank you.
The locking bandwidth is not limited by the lifetime. You can drive with a high Rabi frequency, and if we have a higher energy, strontium itself has a long lifetime of 160 seconds, and yet we can lock it at every hertz or something. It's just depending on how you do state readout, right? Yeah. The long lifetime doesn't mean you cannot read out faster. Any other questions? If not, it's like a super on time, like 5 o'clock. We'll end the colloquium. Thank you, Chuankun.
Thank you.